Hey, welcome to the Mathematics channel, where we are addicted to numbers. Today's video is going to be about standardization and normalization, and what are the differences between the two. If you've been wondering what exactly do these two terms mean, then you've come to the right place, because we are about to explain it clearly, intuitively, and very, very thoroughly. Let's begin. Before we get into the nitty-gritty of what exactly these two terms mean, let's try and understand why we even need either of them. Standardization and normalization are not too different. They fall under the same broad category called data scaling. Let's see data scaling in action. Let's say you have two sports persons. One is Maria Sharapova. I probably butchered that pronunciation, but let's move on. And another is our GOAT. Let's say that Maria scored 15 points in her recent tennis match. And Messi, he scored 5 goals. Now, for those of you unfamiliar with tennis, every single score or every single win or point scored against their opponent is equal to 15 points. Basically, they count in 15s. They're kind of weird like that. And in soccer, every single goal is worth 1 point. Knowing this information, we can clearly see that Maria performed pretty poorly. She performed below average, or she had a bad day that day. Whereas Messi, he performed extremely well, as is expected of him. But if we presented this data to somebody who has no idea what any sport is, then they would probably think that Maria played much, much better than Messi. Let's see what happens when we standardize the data. Don't worry, you do not need to know what standardization or standardizing the data means. Let's just see what happens. Looking at the new values after standardization, we can clearly see that Maria performed below average. She has a negative score, whereas Messi performed quite above average. He has a greater positive score. We can clearly compare the data and just generally understand it much better after scaling. Let's look at a more concrete example in machine learning. Let's say Mr. Black wants to buy a house. Why does he want to buy a house? I don't know. What's he gonna do in the house once he buys it? I still don't know. But it's probably gonna be something legal and neighborly. He's a good man after all. Now let's say that Mr. Black wants to buy a house in a very shady neighborhood. So he does not have the actual data of houses in that neighborhood. Let's say he wants to develop a machine learning model that can predict the price or predict any other feature about the house in that shady neighborhood, even though he does not really have the data. To do so, he will have to train a machine learning model using housing data of various known houses. Let's take a snippet of that data. This is the housing data. Every row represents a house, A, B, C, D, E, and the various data related to that house. We can clearly see that values of various features like price, age, and size are vastly different. Size is in the thousands, age is very low in the 10s or 20s. This is actually very normal for ages. A house would not be 2,000 years old. And the price is in lakhs of rupees. or millions of rupees. Using this very data or unscaled data to develop a machine learning model will be very, very difficult. Basically impossible. Why? Well, this all boils down to the simple model. Say it with me. Machine learning is just fancy math. Lots of machine learning algorithms depend upon linear algebra or linear combinations, as well as distance functions. Basically, a lot of the data used in machine learning models and to train these models relies on these scales of the data. In general, bigger data gets more importance, even if it does not deserve that importance. Let's try to understand using a simple example. Let's take our same data and plot it on a graph. Let's take just the price and the size of every house and plot it on a simple graph. Now, to understand the importance of data scaling, let's zoom in on this graph. Let's zoom in on this portion. After zooming in on this portion, we can see that the size and the price are on completely different scales. Let's say we wanted to perform clustering on this data. Clustering is a machine learning algorithm that basically groups nearby points. Let's say we add a new point to this data. This point is 5% greater in size, which means this point represents a house that is just 5% greater in size. The clustering algorithm, in general, would probably group this with our original point. Let's plot another new point. This time, it's 5% greater in price. This point represents a house that is just 5% more expensive than our original point. A good clustering algorithm would probably assign this house to that same cluster and group all these three houses together. But if we look closely at the data, we can see that this value, even though it's just a 5% increase, it is equal to 140,000 rupees or 1,40,000 rupees. This is quite a lot. The size, on the other hand, has only increased by 50 square feet. The value is just 50. Most clustering algorithms rely on a distance measure, so these values will be directly compared. And naturally, these 2 points will form a cluster, since they're quite close, and this point will form its own cluster off screen with some other point. We can clearly see that the price separated the clusters. The price was the one that decided, no, we are going to make a new cluster. We're not going to be a part of that one. This gives price unnecessary importance. It was just a 5% increase in price. What makes that more important than a 5% increase in size? Why does that get to be a new cluster? These are some of the issues that arise when we work with unscaled data. Let's scale our data now and make everything lie on a similar scale. Our new point is a similar 5% increase in size. And let's plot a new point, which is a 5% increase in the price. Now, most clustering algorithms would group these 3 points as being similar types of houses. And this makes much more intuitive sense. That is what happens when we scale the data. Specifically, in this example, we do not use standardization or normalization. We just simply scale the data very, very directly. But this is exactly what standardization and normalization does. One rather dense and mathematical example is how gradient descent performs with and without data scaling. We can see that when the features are not scaled, we get uneven contours in the feature graph or the gradient descent graph. When gradient descent is performed, it does not follow a straight or proper path towards the minima. It bounces around. On scale data, however, it is more circular. The contours are much better shaped, and gradient descent can find its way in much more easily. For those of you that did not understand this too well, do not worry. This is just for those of you really deep into machine learning. And gradient descent is used everywhere throughout machine learning, whether it is in simple algorithms or complicated ones. So this is another very important example. Credits to Andrew Ng for this graph. His explanation of feature scaling and its importance is in the link in the description below. For those of you who are playing Subway Surfers on the side or some shit, this is a summary of everything we have learned so far. We use feature scaling to make different features comparable so that machine learning models can learn fairly, efficiently, and accurately from data with mixed values or ranges. Now, we are ready to truly understand what both of these terms mean. Let's look at standardization first. Let's use the housing data in our previous example. Now, let's focus on the age column. In practice, we feature scale or we standardize every single feature or every single column in our data set before performing our machine learning. But for simplicity's sake, we're just going to focus on the age column. The process is exactly the same. Let's convert this to a simple number line. Let's plot all of our distances or all of our values on that number line. Now, we have a number line representing the age column of our data set. Let's look at this line. The 0 and the 50 on this number line is just the upper and lower edges. Our actual data lies on this red line over here. This is the age data. Standardization is calculated using this fancy formula. But don't worry, we are easily going to understand what this formula means. Standardization Z is equal to x minus mu upon sigma. Let's look at each of these terms and understand what they mean, and then we'll be able to understand how they function in this formula. X refers to every single point of our data, so 5, 8, 10, 20, and 30. The standardization z-score is calculated for every single point of the data, so the formula you're seeing right now is just the calculation for one data point. Now, let's try and understand what mu means. Putting standardization aside for some time, let's focus on mu. Mu refers to the mean of the data. I'm sure all of you have learned already what a mean is, but for those of you unfamiliar, mean is the average of the data. You sum all of the data and you divide it by the number of data points. So, it is the sum of xi, basically the sum of every single data point, divided by n, which is the number of data points. Calculating it for this data, we get the value 14.6. Let's focus on our second term, sigma. Sigma is the standard deviation. Now, for those of you who do not know what a standard deviation is, this formula might seem very daunting, but do not worry. Standard deviation is just the root of the average squared difference between every single data point and the mean. What does that mean exactly? Well, you take every single data point, xi, and you subtract the mean from it. Whatever value you get could be positive or negative. For example, if you took 10 and subtracted it from the mean, that would equal to minus 4.6. Negative values are troublesome, so we just square it so that every value is positive and the differences are emphasized. We sum this up for every single data point, calculating the difference between it and the mean and squaring it. After summing up for every single data point, we take the average. Rooting this to negate our square, we get the standard deviation. For this data set, the standard deviation would be 10.29. Standard deviation tells us, on average, how above or below the mean the data points are, kind of the spread of the data points around the mean. Knowing these terms, we can now understand what standardization exactly means. We are subtracting the mean from every single data point and dividing it by the standard deviation. To understand why, let's look at what standardization does to our data. Specifically, our little red line that we have made to represent our data. Let's look at the first part of the standardization formula, which is x minus mu. This basically means subtract the mean from every single data point. Let's see what it does to our data. Ignoring the numbers for now, let's just look at our data points and the line representing the data. After subtracting the mean from every single data point, all the data points are shifted such that the new mean is 0. This moves our data back towards 0 as its mean. Why? Because when you subtract the mean from the mean, the answer is 0. Since we've subtracted the mean from every data point, the new mean has also been shifted to minus the mean, essentially 0. Our new data is now represented below. Our data is averaged around 0. Let's look at the next part of our formula. We are about to divide by the standard deviation. Our standard deviation has not yet changed because we have just moved our data backwards. Since adding or subtracting from all of our data points moved our entire line forward or backward, in this case backwards on the number line, can you guess what dividing would do? Yeah, dividing would shrink or compress our line, our little red line, so that it is much smaller than what it currently is. If we divide every single point by the standard deviation, dividing every single point by the standard deviation makes it so in our standard deviation calculation, the standard deviation itself is divided by the standard deviation. That would make our new standard deviation equal to 1. Let's see it in action. Looking at our new line, we can see that our standard deviation is now 1, and everything is centered around 0. This was the main goal of standardization, to represent all of our points at some distance comparable to the standard deviation. Since our standard deviation is 1, comparing all of our points and how far they are from the mean is very easy. Since our mean is also at 0, negative points are below the mean and positive points are above the mean. Before, every point was positive, so we had no idea of whether it's below or above the mean if we did not know the mean. Right now, even if we did not know the mean, we know the negative points are below it and positive points are above it. And similarly, even if we do not know the standard deviation of our actual data, looking at the scale data, we can easily tell which points are far from the mean and which points are close to the mean, or which points are above average or just about average. So, standardization in a nutshell is shifting our data so that the mean is now 0 and then squashing it down such that the standard deviation or the spread of the data is 1. Comparing it to the data that we had before standardization. One very common myth is that standardization makes the data follow a normal distribution. A normal distribution means that points are evenly separated around the mean. We can clearly see that this is not the case. Our data points are not normally separated around the mean. They're quite unequally separated around the mean. This is very far. This is pretty close. So we do not convert our data into normal data. It just scales the data in such a way that the new mean of the data is 0 and the standard deviation is 1. This allows us to gain much more insight into the statistical value of the data and compare it to other standardized data without knowing the scale. We can also see that we do not change the original shape of the data. Looking at our original data, the shape of our data points is also exactly the same. Our data looks just about the same, it is just shifted and shrunk. In statistics, way before machine learning, Z or Z distributions or Z scores was a very common term used to represent or calculate how many steps or how far from the mean any data is in terms of the standard deviation. Basically, how many standard deviations are you away from the mean? For example, this point is 1.4 standard deviations away from the mean. Since this number line now represents how many standard deviations away it is, since 1 would equal 1 standard deviation away from the mean. That's because our standard deviation is 1. This is also why standardization is called Z-score scaling. Now that we've understood standardization, let's take a look at normalization. You'll be pleased to know that normalization is much more easy. But before that, let's rewind back to our housing data. Now that we're back at our housing data, let's take the same column and the same graph which represents that column and perform normalization. Using the same little red line to note our data and exactly what our data is, let's calculate normalization. The formula for normalization actually does not look too daunting, so let's simply dive into it. X, just like in standardization, refers to each and every data point that we have. So 5, 8, 10, 20, and 30. X min refers to the minimum value or the minimum data point that we have. Looking at our data, we can easily see that X min would be 5. Let's highlight it. Similarly, I'm guessing you already know what X max would refer to. X max refers to the maximum value of data. Let's look at the upper terms and the lower terms separately. You may notice that the lower term, X max minus X min, means you're taking the highest value of the data and you're subtracting the lowest. So basically, you're getting on what line does the data lie. We can clearly see that X max minus X min literally gives us our red line, since our red line represents the range of the data. Let's see, similar to how we did in standardization, what normalization does to our little red line. Looking at the above part, X minus X min, we subtract the minimum value from every single point of our data. Let's see what it does to our little red line. Ignoring the actual values, let's see what happens. We've just subtracted the minimum from every single point of the dataset. So basically, our new minimum would be 0, since for our minimum, the top part of the equation would be X min minus X min, which would be 0. We have basically shifted our little red line so that it starts from 0. These are the new values that we get after. subtracting the minimum. Let's focus on the second half of our equation. The second half would be dividing our little red line by itself. Whenever you divide anything by itself, the answer is always 1. Since we're dividing, we are compressing or shrinking it down. So basically, the entire little red line will be shrunken down so that its value is 1. So all our data points lie between 0 and 1. This is why, in linear algebra, normalization also means dividing a vector by itself, because that is essentially what we're doing to the data. Once the data is shrunk, let's look at the new values of our data. They're all between 0 and 1. Our new maximum value is 1, since when we take the maximum value and put it in the equation, we subtract it from the minimum and divide it by the same thing. So, both of these parts would cancel out and become 1. Comparing it to our original data, we can clearly see that the shape of the data has completely changed. We have squashed everything down to between 0 and 1. The new values represented after normalization basically tell us how much progress have I made from the minimum to the maximum in my respected data column. So, this point is around 60% ahead of the minimum and between the minimum and the maximum. This point is 20% between the minimum and the maximum. Since we use the minimum and the maximum in our equation, this is why normalization is also called min-max scaling. So, we've taken our data in various different scales, and we have performed standardization and normalization to get much more intuitive and clear representations of the data. We can clearly see the difference between the two just by looking at the distributions. Normalization brings the data between 0 and 1 and squashes it, whereas standardization does not bring it between 0 and 1. It is theoretically in an infinite range, which means the values after standardization can be very large or very small as well, depending on the data set. Both of them have their own different use cases. When we want to bring data to be comparable in terms with the average or the mean and the standard deviation and other such statistical values, we perform standardization. And when you want to bring the data into a specific range, usually between 0 and 1, we perform normalization. And now our machine learning models are going to learn much better. Hooray! One important difference between standardization and normalization is how each of them handle outliers. Outliers are basically data points that are unusual or very large or very small. They have values that are not similar to the other data points. Let's take an example. Starting with standardization, let's go back to our housing data. Let's say instead of 30, we had 120. This is an outlier. To accommodate this, we had to change the scale of the data as well, so do not be alarmed. We've just made it from 0 to 150 instead of from 0 to 50. Let's see what happens to this data after standardization. Taking our little red line, we are taking our little red line from much better what the standardization formula does to our data. To calculate the standardized values, we need to know the new mean and standard deviation of our data. We can see that the mean and the standard deviation have increased significantly. Performing standardization on our data, we get this new line. We can see that we have performed the exact same thing as before by shifting the entire little red line so that the mean is 0 and compressing it so our new standard deviation is 1. We can see that our outlier is still an outlier and our data shape is still the same. The value pertaining to 120, which is all the way on the far right over here, is still quite separate from the rest of the data points, so our outliers are maintained. In contrast, let's see what happens when we perform normalization. To calculate the normalization, we're going to need the minimum values as well as the maximum. Our new maximum value is our outlier. Since the definition of an outlier is that it is very different, very large, or very small compared to the rest of our data. Performing normalization or min-max scaling, let's see how our data is manipulated, or how our little red line changes. We can see that the same thing happened as before. Our little red line has been shifted so that the minimum is at 0, or so that it starts at 0, and it has been compressed so that it is now very teeny and lies between 0 and 1. We can clearly see that the outlier has not been retained. After normalization, it is now 1. Before, the value 80 was equal to 1. So, the fact that our outlier is equal to 1 does not tell us any information about whether it's an outlier or not. It just means it was the maximum value, not whether it was an outlier. We can see it is quite far apart from the data, which could characterize it as an outlier. But the negative is that all of our data is now squished in this tiny zone between 0 and 1, and is not as informative as it would have been had there not been an outlier. So, normalization does not handle outliers as well as standardization. We can clearly see this if we compare both of the bars or little red lines that we got from standardization as well as normalization. We can see that the shape of the data and where the outlier is has been maintained by standardization, whereas normalization squashed everything down and compressed it all. This is because although in standardization the mean is affected by the outlier, it is not as affected as normalization, where the min or maximum value can directly be an outlier. Standardization handles outliers better than normalization, but it still does not handle them 100% well. For that we have robust scaling, where we use the median instead of the mean, and we use the interquartile range instead of the standard deviation. But that is beyond the scope of this video. Let's look at some of the differences between normalization and standardization. This is a table of their important or general differences. We can see that the uses for normalization and standardization vary on the machine learning application. The machine learning applications that require values in a specific range prefer normalization, whereas ones that require a Gaussian distribution or a normal distribution use standardization, since that relies on the statistical calculations like standard deviations and means. If you've reached this far in the video, I hope you've learned something new and can now easily tell the difference between normalization and standardization,